Anatomy of a Formal Proof by Jeremy Avigad, Johan Commelin, Heather Macbeth, and Adam Topaz. I'm Dr. Samuel Alan Alexander, mathematician and philosopher, still here, and I'm reading this article published in 2025 in the notices of the AMS. And I have a connection with Jeremy Avigad, the lead author of this paper. One of his students oversaw the undergrad paper that I wrote, which was published in the Rose-Hulman Undergrad Math Journal in 2006. Anyway, introduction. It has been a long day and you are making your way through a paper related to your work. You suddenly come across the following remark. Since x and y are eigenvectors of f with distinct eigenvalues, they are linearly independent. Wait, how does the proof go? You should really know this. Here x and y are non-zero elements of a vector space V, and f v to v is a linear map. You force yourself to pick up a pen and write down the following argument. Let f of x equals mu x and f of y equals nu y with mu not equal to nu. Suppose ax plus by equals 0. Applying f and using linearity, we have mu ax plus nu by equals 0. Multiplying the original equation by nu, we have mu ax plus nu by equals 0. Subtracting the two yields mu minus nu quantity ax equals 0, and since mu minus nu and x are non-zero, we have a equals 0. The corresponding argument of the x and y swapped yields b equals 0, so the only linear combination of x and y that yields 0 is the trivial one. That works, doesn't it? Your colleagues have all gone home and there's nobody around to discuss this with. So instead you turn to your computer and start up Lean, the proof assistant you happen to use. Can you prove the claim formally? As you type, the information window in your editor complains about every misstep. The syntax is fiddly, and you have to get the notation and the instructions just right. But that's okay because working through the proof is relaxing and kind of fun. This was written in 2025. Already in 2025, for this particular situation, a large language model would be a far better way to approach this rather than Lean. Of course, the large language model is liable to hallucinations, but in this example where you have a proof and are merely wanting to check it, it would be a ton less work than doing this in Lean. Anyway, the authors continue writing. Lean often makes you spell out arguments that are painfully obvious, but you've found that if you set things up just right, it'll cheerfully fill in some of the details. After a short while, you have success. Lean signs off on the proof, confirming you've managed to construct a formal derivation in the system's axiomatic foundation. Import mathlib.linearalgebra.linearindependent, variable bracket field k, bracket add com group v, bracket module kv. Example, f has type v, right arrow sub l, bracket kv. I don't know how you would type the sub l. Mu nu have type k, h mu nu have type mu not equal to nu. xy have type v, hx0 has type x not equal to 0, hy0 has type y not equal to 0, hx has type fx equals mu dot x, hy has type fy equals nu dot y. For all ab of type k, a dot x plus b dot y equals 0 implies a equals 0 and b equals 0. Defined it to be equal by intro ab have defined it to be calc mu minus nu quantity dot a dot x equals a dot mu dot x plus b dot nu dot y quantity minus nu dot left parentheses a dot x plus b dot y right parentheses colon equals by module underscore equals f left paren a dot x plus b dot y hyphen nu dot left paren a dot x plus b dot y right paren colon equals by simp hx hy underscore equals 0 colon equals by simp hab simp all sub equals 0. What a lovely proof. I'm not sure if the authors are being sarcastic here or not. They continue. It took some effort to work it out, but it was a pleasure seeing the steps play out formally, and you are proud of the result. Understanding the proof. Let's take a look at what you've done. You are using Lean's mathematical library MathLib, a communally developed and maintained repository of formally verified mathematics. At the time of writing, MathLib contains more than 80,000 definitions and more than 160,000 theorems, starting from axiomatic primitives and developing mathematics from the bottom up. It also contains dozens of user-contributed automated reasoning procedures that help with the formalization process, as well as notation, declarations, and configuration information, all of which codify different aspects of our mathematical understanding. To avoid having to load the entire library into memory at once, Lean asks you to tell the system what parts of the library you want to use. Well, that's not just to avoid loading the entire library at once, that's also to avoid name collisions. Anyway, they continue. So the first line of the proof, the one that starts with the keyword import, tells Lean you want to use the file with the name shown. That pulls in all the files of the library that those notions depend on, which is quite a lot, including basic algebra, properties of scalars and vectors, and so on. The next line, the one that begins with the word variable, declares some of the objects you want to work with: a field, k, and a vector space v. You could have alternatively put these declarations after the example keyword on line 5. Using the variable command to declare them separately is especially convenient when multiple definitions and theorems share the same data and hypotheses. It's a quirk of the library's design that you declare that v is an additive commutative group coupled with a scalar action that turns v into k module. Remember, a vector space is nothing more than a module over a ring in which the ring in question is actually a field. MathLib includes thousands of axiomatically declared structures, and the contributors to the library take great care to maximize reusability by breaking structural hypotheses into reusable pieces that can easily be configured and composed. Next comes the keyword example, line 5, which indicates that the result you're proving is not intended for future use. Using example is good for experimentation. To prove a lemma or theorem that you intend to use later, you would instead use lemma or theorem and provide a name. In that case, once Lean has processed the proof, it's stored in the environment, which means that any file that imports this one can see it. If you think you have proved a theorem that ought to go into MathLib, you can issue a pull request to add it to the library. MathLib is overseen by teams of maintainers and reviewers who moderate and update the contents, ensuring the quality and stability of the library. You begin stating the claim by introducing the key players, a linear map f from v to itself. Lean's notation for such linear maps is v right arrow sub l bracket k close bracket v. Again, that sub l, I don't see a sub l anywhere on my keyboard here. Two elements of k denoted mu and nu, which will end up being your eigenvalues, and a hypothesis called h mu nu that says mu and nu are distinct. Two vectors called x and y, as well as hypotheses hx0 and hy0 that say they are non-zero. And finally, your two key assumptions, hx and hy, which say that f of x equals mu x and f of y equals nu y. In the notation v right arrow sub l bracket k close bracket v, the sub L is a fixed symbol signifying linear maps, whereas the parameter in brackets indicates that we mean linearity over K. At this point, you have set up your context, that is, the data and hypotheses you need to state your claim. You have your K vector space V, a linear map f v to v, two scalars mu and nu, and eigenvectors x and y for mu and nu respectively. At that point, you are ready to state the conclusion, lines 9 and 10, namely, that x and y are linearly independent. For all ab of type K, a.x plus b.y equals 0 implies a equals 0 and b equals 0. You have decided to use the definition of linear independence for a pair of vectors. Whenever a and b are scalars, if a times x plus b times y is 0, then a equals 0 and b is 0. Notice that you have used the symbol colon in expressions like xy has type v, line 7, to express that x and y are elements of v, rather than writing x in v and y in v. In Lean's axiomatic foundation, a version of dependent type theory, every object has a fundamental data type. In this example, we would say that x and y are terms of the type v. Interestingly, we use the same notation in an expression like hx0 has type x not equal to 0, also line 7, to express that hx0 is a label for the assumption x not equal to 0. In dependent type theory, assertions like x not equal to 0, also known as propositions, are analogous to data types, and they are handled by the same fundamental mechanisms. Lean checks that an expression like a.x plus b.y is a well-formed expression of type v, given information about the variables and symbols involved, and in the same way it checks that a formal expression is a well-formed proof of the proposition for all a b of type k, a.x plus b.y equals 0 implies a equals 0 and b equals 0, given the data and assumptions it depends on. That is why the latter appears with colon in the example's conclusion. The statement of the example announces your intent to construct a formal proof of the conclusion, given the data and assumptions that come before. What comes after the symbol colon equals, line 10, is the proof itself, or more precisely, instructions that tell Lean how to construct the proof. If you're successful, the corresponding expression is stored in memory and checked for correctness by Lean's trusted kernel. The keyword by after the colon equals instructs Lean to enter tactic mode, which means that the text that follows should be interpreted as a list of instructions that tell Lean how to build the required proof. A tactic is a procedure that automatically fills in a chain of formal inferences that's needed to justify a reasoning step. Such a chain can be as short as a single logical axiom or rule, but it can also be quite long and involved. Tactics thus play an important role in bridging the gap between the kind of reasoning that's intuitively clear and natural to mathematicians and the stringent axiomatic rules embodied by a formal system. The first tactic you use is intro AB HAB, line 11. This introduces the two variables A of type k, B of type k, which your statement quantifies over, as well as the antecedent to the implication, that is, the assumption HAB, A.x plus B.y equals 0. As you type or move your cursor around a proof, Lean displays the tactic state, i.e. information that is relevant at that point in the proof, in its info view window. After the intro tactic, the tactic state looks something like this. K is a type, V is a type, F has type V, right arrow sub L, bracket K, close bracket V, mu nu type K, H mu nu type mu not equal to nu, XY type V, HX0 type X not equal to 0, HY0, Y not equal to 0, HX type Fx equals mu dot X, HY, Fy has type HY says HY has type Fy equals nu dot Y, AB has type K, HAB has type A dot X plus B dot Y equals 0, turnstile A equals 0 and B equals 0. Turnstile A equals 0 and B equals 0. This is a nice summary of where you are in the proof, including the objects and assumptions you started with, as well as the objects A, B, and the assumption HAB that you introduced in the first step. The line that starts with turnstile indicates that your current goal is to prove the conjunction A equals 0 and B equals 0. While writing the proof, you notice that Lean complains with warnings and error messages. This is expected since the proof is incomplete. You can appease Lean by apologizing for the incomplete proof. If you use the sorry tactic on the final line of the proof, Lean will not raise an error over the fact that the proof is incomplete, but it'll still raise a gentle warning about the use of sorry. The next step of the proof starts with have defined to be calc, line 12. This introduces a calculation similar to a begin a line star, end a line star block in LaTeX. The calculation itself is very similar to the one in the proof sketch above, but notice that the individual steps in the calculation are justified by short subproofs like by module or by simp. The module tactic proves equalities of universal linear expressions, in other words, linear equalities that are true in all modules, and do not use specific facts about the module at hand. The simp tactic is a powerful tool that uses a database of equalities and equivalences from MATLib, together with user-specified equations like hx, hy, to rewrite its goal into a simpler form. Happily, in this case, the goal becomes a trivial equality, and the goal is therefore closed. In a moment, we will consider the steps that simp has taken in greater detail. After this calculation, you completed your proof with the simp all tactic, which is a variant of simp that recursively uses all the hypotheses to simplify all hypotheses in the goal. Now, if you leave a sorry after the simp all, Lean will complain that there's nothing to be sorry about and insist that you remove the apology. Lean checks the correctness of the proof and confirms it with its silence. The absence of errors is the proclamation you've succeeded. Using automation. So what exactly does the simp tactic do? The following provides a manual, more detailed proof of one step of the calculation in your proof with the direction of the equality reversed. I'll skip all this soup since it's machine generated. This example demonstrates the rewrite tactic, denoted RW. In the calculation, we first rewrite with the lemma map add, which states that for any linear map f, the equation f parentheses v plus w close parentheses equals fv plus fw holds. The next step in the calculation is justified by rewriting twice with the lemma map small, which states that for any linear map f, scalar c, and vector v, the equation f parentheses c dot v close parentheses equals c dot fv holds. Here small stands for scalar multiplication. The underscores before each subsequent step are part of the calc syntax, indicating to the parser that the calculation continues. The proof concludes by rewriting with the hypotheses hx and hy, which assert that x and y are eigenvectors of f with eigenvalues mu and nu respectively. The lemmas map add and map scalar multiplication are part of the mathlib library, and they're labeled with the attribute @simp. This attribute tells Lean that the lemmas should be added to the database of lemmas that simp uses to simplify expressions. And that is the reason why the simp tactic could prove the goal in one go. It chained together the RW steps that we spelled out step by step in the calculation above, the rewrite steps that we spelled out step by step in the calculation above. One of the challenges of formalization is that we often need to spell it out in painful detail inferences that seem obvious or straightforward to us. The more we can get the computer to fill in, the better. The simplifier is an important example of automated reasoning that can help in this respect. The module tactic is another. Well, again, it's the year of our Lord 2026. You just tell an AI to generate the proof for you, or in this particular example about being at work and wanting to prove this fact from linear algebra, you write that proof send that to the AI and ask the AI to translate it into Lean for you. Anyway, the authors continue saying, broadly speaking, there are two classes of automation. Firstly, there is a general purpose automation. One example that we've seen is the SIMP tactic, the simplifier. Another example is ASOP, a tactic that provides automated extensible search for obvious proofs. In the proof assistant Isabel, there's a tool called Sledgehammer, which can search for proofs using a large database of lemmas. And recently, AI copilots have demonstrated the ability to suggest tactics and fill in parts of proofs in Lean. This was in 2025. The situation has become much more so now in 2026. In fact, recently, AIs have actually have solved certain open problems. Anyway, the authors continue saying, the wide applicability of these general purpose tools is balanced by the fact that at least for now they can only assist with proofs that are relatively straightforward. The other class of automation is domain-specific automation. Here we have also seen an example, the module tactic. Other examples include the ring tactic, which solves equations in commutative rings, the linarith tactic, which solves linear arithmetic problems, and the funprop tactic, which proves that functions satisfy given properties such as continuity or measurability. These tactics are less general. They typically have a well-defined and narrow scope, but they can be very powerful in their domain of applicability. A prime example of this approach comes from the use of software tools known as SAT solvers and SMT solvers. If a claim can be encoded as a Boolean formula or formula in some decidable theory, then these can be used to justify it automatically. This has been fruitfully applied in non-trivial ways. Generalizing the hypotheses. Often, one of the first things we do when we have proved a lemma or a theorem is check whether the hypotheses can be weakened in order to increase its applicability. Proof assistants are especially helpful in this respect because they enable us to tinker with hypotheses interactively and see what breaks. Returning to our example, upon verifying the initial result, you might wonder, what are the minimal assumptions that we need to make this proof go through? Let's experiment. The proof never mentions inverses of scalars, so it should work for a larger class of rings. In a first attempt, we might try to replace the vector space V by an arbitrary module M as follows. Variable Rm are types, ring R, add common group M module Rm. But Lean complains that the first step of the calculation, which requires b.new.y equals new.b.y. We can address this by assuming that the ring of scalars is commutative. However, after making that change, the final step of the proof is still broken. A bit of reflection shows that this step uses the result of the calculation steps together with the assumption h mu nu, mu not equal to nu, and hx0, x not equal to 0 to prove that a equals 0. In other words, we need the additional property that r.m equals 0 implies that r equals 0 or m equals 0 for every r in the ring and m in the module. MATLAB expresses this as the property no zero scalar multiple divisors rm, and we can add that assumption as follows. More code, which I won't read out loud. Lean accepts this statement of the same proof as before. We have therefore obtained a more general theorem without changing a single character of the proof. Strengthening the theorem. Let's see if we can strengthen your result even further. You started with the basic version involving vector spaces over fields and only two eigenvectors, and we just generalized it to suitable modules over commutative rings. Where can we go from here? Let's try to generalize the theorem to arbitrary families of eigenvectors. To do this, we'll need to think carefully about how to express in Lean the fact that an arbitrary family of vectors is linearly independent. We could write down a definition from scratch, but it makes sense to see if we can take advantage of things that are already in the library. If we navigate to the MATLAB documentation webpage and start typing linear independent in the search box, one of the first few results that comes up is the following. Def linear independent, iota type, R type, M type, V iota to M, semiring R, add commutative monoid M, module Rm, prop. Here R and M are the relevant ring and module as before, iota is an indexing type, and V is a family of elements of M indexed by iota. It is standard and convenient to represent a family Vi in iota of elements of M as a function V from iota to M, in which case the ith element Vi is simply written V space I. All the arguments in curly and square brackets are generally left implicit, which is to say, we expect to write linear independent RV and to have Lean figure out the rest. The annotation prop means that the expression linear independent RV is a proposition, namely the proposition that the family V is linearly independent over R. At the moment, we don't need to know the body of the definition, we can use it as a black box. To do so, we'll add an indexing type iota to the statement of our theorem, and since we also want to say that the vectors are all eigenvectors, we will also use iota to index a family mu of scalars which will act as the eigenvalues. We can now formulate the statement we are after as follows. More code which I won't read out loud. Note that we have formulated the fact that we are considering distinct eigenvalues by assuming mu is injective. We should check to see whether something like this theorem is already in the library. If we go back to the documentation webpage and search for eigenvector linear independent, only 2 results come up. Lots of code. The difference between the two is that the first is about a set of scalars and a function assigning an eigenvector to each scalar, whereas the second one is about indexed families of scalars and eigenvectors. The second one is more promising for our application since we also chose to use indexed families of vectors and scalars. To use this theorem to prove our version, we invoke the apply tactic. This leaves us with a number of goals. Function.injective question mark mu, asking us to prove that something is injective. For all I of type iota, question mark f dot has eigenvector question mark mu I space vi, which looks like it should have something to do with our assumptions h and hv. Module.end rm, asking us to provide an endomorphism of m. This should just be our linear map f. And finally, iota to r, which will be our mu. The question mark mu in the first 2 goals and the question mark f in the second goal mean that Lean does not yet know how to instantiate the variables mu and f in the theorem we've invoked. It left those tasks as the 3rd and 4th goals. Lean expects that it'll be more convenient for us to provide that information implicitly when we solve the other goals. We've made progress, but we still need to provide the information requested. We should clearly use h mu to solve the first goal, which we do by adding the next line to our proof. Apply module.end eigenvectors underscore linear independent prime exact h mu. As you might guess, the exact tactic tells Lean to use the assumption h mu to close the goal. As a side effect, that also closes goal 4. Lean is now able to infer that the family in question is mu. We then have 2 goals left. For all I of type iota, question mark f dot has eigenvector mu I space vi and module.end rm. We know that the endomorphism of m should be f, so we swap the order of the goals and give Lean this information. Apply module.end eigenvectors underscore linear independent prime exact h mu, swap semicolon exact f. This leaves us with one last goal, namely, for all I of type iota, module.end.has eigenvector f mu I space vi. We need to make our assumptions h and hv, but it's unclear how to package them together to satisfy the definition of module.end.has eigenvector. Instead of going back to the documentation page and looking up the definition, we can ask Lean what we have to do. Some more code. As before, the intro tactic introduces an arbitrary I, and then the constructor tactic tells Lean that we're ready to provide the information needed to show that vi is an eigenvector of f with eigenvalue mu I. This makes progress, but we still have the following goals to fulfill. vi in module.end.eigenspace f of mu I, vi not equal to 0, which is obviously an application of hv. For the first goal, vi in module.end.eigenspace f of mu I, the hypothesis h has type for all I f of vi equals mu I dot vi should do the trick, but applying it directly doesn't work. After digging into the details, we see that this is because the eigenspace of f with respect to a scalar mu is defined as the kernel of f minus mu dot 1, so we'll need to convert h to this form. We could do this manually, but we can first check whether we can use a pre-existing lemma from the library. The fastest way to do this in the middle of a Lean proof is to try the exact question mark tactic. This will do a search for ways of applying existing lemmas to close the goal exactly. This tactic doesn't always work, but it can't hurt to try. Aha! In this case, it tells us right away that we can close the first goal by writing exact module.end.mem underscore eigenspace underscore if dot mpr space hi. The second goal is also easy to close by applying hv, so now we have a complete proof, which I will not read out loud. The beginning of our proof was a bit messy, but we can clean things up to obtain a nice final result. Another big block of code, which I will skip. The apply tactic now supplies f, mu, and h mu right away, leaving only one remaining goal. We've thus achieved the level of generality we were after. Should this theorem be added in MathLib? Upon consideration, we should conclude that our theorem is not substantially different from module.end.eigenvectors underscore linear independent prime. In our proof, we only added some plumbing and changed the way we talk about eigenvectors to match the theorem in the library. Now that we know about module.end.has eigenvector, it seems that this is the standard way to talk about eigenvectors in MathLib. If we were to modify our statement to use this instead of our bespoke h and hv, our theorem would be a direct application of module.n.eigenvectors underscore linear independent prime. In other words, we have come to realize that the theorem in the library is what we really wanted all along. But the good news is that we have learned a lot in the process, and we are now much more comfortable reasoning about linear independence and eigenvectors with MATLAB. Using version control. Programmers and computer scientists have long made use of version control platforms like GitHub to work on large collaborative software projects. Formalization has brought the same tools and methodologies to mathematics. At the time of writing, MATLAB comprises approximately 5,000 files and 1.5 million lines written by over 300 contributors. These contributions go through an open review process on GitHub before they're merged into the main repository. In total, there have been a bit more than 30,000 contributions since MATLAB's inception in 2017. A nice thing about version control tools is that they maintain the entire history of the project, allowing us to see what's changed and when. For example, we can trace the history of the concept of linear independence in MATLAB. It all started on December 7, 2017, when Johan committed the file algebra/linear-algebra-basic.lean to the repository. The file was 708 lines long, and on line 186 it contained a definition of linear independence. The terms L quantify over LC alpha beta, the type of all linear combinations of elements of beta with coefficients in alpha. On March 10, 2018, an administrative operation moved linear_algebra out of algebra so that it became a top-level folder. Another such move occurred on January 15, 2019, when Simon Hudon moved all the mathematical content into source to separate it from the tests and other auxiliary files. It took them 2 years to do that. On July 3, 2019, Alexander Bentkamp morphed the definition into def linear independent prop, defined to be finsup.total iota mrv quantity.cur equals bot. In other words, a collection of vectors v in M is linearly independent if the natural map from the free module generated by the vectors v to M has trivial kernel. Then on October 5th, 2020, Anne Bannon split linear independence and the accumulated supporting theory into a separate file, source/linear-algebra/linear_independent.lean. The file was 918 lines long. The story continued on February 23, 2023, when Polta/Miyahara Co. ported the file to Lean 4 as part of a massive collaborative effort to move all of MATLAB to the new version of Lean. The file name is now matlab/linear-algebra/linear-independent.lean, and it lives in the new MATLAB 4 repository on GitHub. The definition has not changed substantially since the change by Bentkamp. Conclusions. The earliest programs for checking mathematical proofs include Nicolas de Brien's Automath system, launched in 1967, wow, that's old, and André Triboulet's Mizar system, launched in 1973. Since then, dozens of proof assistants have been developed. Coke, Isabelle, and Whole Light are among the more prominent ones still in use today. The Lean project, launched by Leonardo de Mora in 2013, is a relative newcomer. A special issue of the notices with articles by John Harrison, Thomas Hales, and Freek Wieddijk surveyed the state of the field in 2008. We have come a long way since then. Proof assistants are now commonly used in industry to verify hardware, software, network protocols, cryptographic protocols, cyber-physical systems, and more. Mathematicians have only recently begun to embrace the technology, and it's becoming clear that there are several benefits to representing mathematics in digital form. Just as the word processor opened up new opportunities for written expression and communication, the digitization of mathematics opens up new opportunities for mathematical research and teaching. The practical benefits are not the only motivation. To many of us, formalizing mathematics feels like the right thing to do. Mathematical definitions and theorems deserve to be rendered digitally. It's also becoming clear that the technology is here to stay. MATLAB currently has roughly 1.5 million lines of code and continues to grow. Important results including foundations for Clausen and Schultz's condensed mathematics, the polynomial Freeman-Rouge conjecture, and an exponentially improved upper bound to Ramsey's theorem have been formally verified before journal referees signed off on them. A number of collaborative verification projects have been launched, including a proof of the sphere inversion theorem, and a proof of a strengthened version of Carlson's theorem on pointwise almost everywhere convergence of Fourier series. We expect that in the years to come, let's look at this footnote 13. It's a link. We expect that in the years to come, AI copilots that combine neural and symbolic methods will significantly ease the burden of formalization. More dramatically, We expect that the technology we have discussed here will play a significant role in the discovery of new mathematics. Note that DeepMind's AlphaProof, which was deemed to have performed at the level of a silver medalist at the most recent International Mathematical Olympiad, was trained to find formal proofs in Lean. It's exciting to think about what a synergistic combination of machine learning, symbolic methods, and user interaction will bring to mathematics in the years ahead. Oh, minor side note, I've actually co-authored a couple of papers with the PhD advisor, Marcus Hutter, of one of the founders of DeepMind. Anyway, the writers continue saying, you can find online documentation and tutorials for all the proof assistants we've just mentioned. Lean's lively social media channel on the Zulip platform is welcoming to newcomers, and the Lean community web pages contain links to learning resources like the natural number game to help you get started. Proof assistants are not easy to use, and learning to formalize mathematics requires significant time and effort. Interaction with proof assistants like Lean comes naturally, however, to those who have grown up immersed in computational technology. We have therefore found that one of the best ways to take advantage of proof assistants is to have our students help us out. Formal mathematics is a language, and only they can claim to be among the first generation of native speakers, while the rest of us struggle to master the grammar and intonation. With all the changes looming, we ought to be concerned about the ways that proof assistants and AI will change the mathematics that we know and love. It is therefore all the more important for those of us who are more settled in our careers to play an active role in the adoption of the new technologies, using our mathematical values and expertise to guide our students as they negotiate the changing landscape. The new developments offer us a wonderful opportunity to lead from behind, and it falls on all of us to support the next generation of mathematicians as they forge a path into the digital future. Acknowledgement. We are grateful to the Hausdorff Research Institute for Mathematics for hosting 3 of us for the trimester program Prospects of Formal Mathematics in the summer of 2024, during which most of this article was written. We're also grateful to Paul Buckingham and 3 anonymous referees for helpful comments, corrections, and suggestions. I think it's kind of a silly article because there's very little hope of anybody really gleaning anything by reading this on paper. You really need to roll up your sleeves and get your hands dirty. I actually did formalize a whole paper of mine back in, I think it was 2012 or so, in response to requests from peer reviewers to do so. I did that in Coke, which has since fallen out of fashion. Now Lean is by far the fashionable automated proof assistant. And that was very interesting, but I wouldn't ever wish on my worst enemies the task of actually reading the code. This has been Anatomy of a Formal Proof by Jeremy Avigad et al. I'm Dr. Samuel Alan Alexander. Please like, comment, and subscribe. I'll see you in the next video.